This is the mark scheme for the Alkanes test. Please watch all of it because you may learn some exam technique in how better to answer some of the previous questions. Please feel free to pause, and if you do want any clarification on any of the questions, please do email your teachers. The reaction between methane and bromine is a free radical substitution reaction. That happens in 3 stages: initiation, propagation, and termination. The ultraviolet light is involved in the initiation process, where it splits or homolytically lyses the bromine molecule into 2 bromine free radicals. So this is the only answer it could be. The ultraviolet light doesn't provide enough energy to break any of the other bonds. Here we're drawing a branched alkane with 4 carbons. Therefore, best to draw 3 first and then figure out where you can put the last branch, or the methyl group, and it can only go in the middle. If it goes on either of the ends, it then becomes part of the parent chain and no longer a branched chain alkane. Now, the molecular formula for this alkane is C4H10. If we react it with bromine, then we have to replace one of the hydrogens with a bromine, therefore we'll have H9Br. This mechanistic step has a free radical at the start and a free radical at the end. Therefore, a free radical is being propagated. Therefore, it is the propagation step. If it was initiation, then you will have 2 free radicals produced, none at the start, so you've got free radicals being initiated, and at the end your 2 free radicals will come together to be terminated, and you'll have no free radicals in the products. So for here, your initiation step can only be C because you have 2 free radicals being produced. It's homolytic fission because both atoms are the same, and it's D because you have 2 free radicals at the start in the reactants and then no free radicals in the products. It can only be D. And then your ethane is produced because of 2 methyl groups, 2 methyl free radicals combining, and they form ethane, C2H6. And your methane, your methyl free radical is produced from your chlorine free radical. So this is proof that there's a propagation step where your free radical reacts with our CH4 to produce your CH3 radical plus hydrogen chloride. And then for F, you'll have to filter out your wanted product because you have a mixture of products. So you can have these answers or any other words that these affect. Okay, so first, finding the name of this structure, we need to find out the name of the parent chain and count the carbons. 1, 2, 3, 4, 5, 6. It's going to be hexane. We have 2 methyl groups, 1, 2. So we need to find out the position of those methyl groups. So it's going to be dimethyl hexane, and this methyl group is on the 3rd and the 5th carbon. So 1, 2, 3, 4, 5, 6. So 3 and 5, or it can be 1, 2, 3, 4. So 2 or 2,4 dimethyl hexane. 2,4 dimethyl hexane is lower, so it's going to be that. Then your structural formula should follow your name, or your structural formula should follow your skeletal formula. And just remember brackets for branches. So wherever you've got a branch, you've got a bracket. So after the 2nd carbon and after the 4th carbon, it should be here for your 2,4 dimethyl hexane. Now your homologous group, any of these it will allow. I don't really like the same general formula. I don't like that one just because you have cycloalkanes and alkenes have the same general formula, which is CnH2n. And that leads us nicely on to C, and cyclopentane does not have this general formula, CnH2n plus 2. So that is the wrong answer. Or the answer that is not true, B. An alkene has 83.7% carbon, and therefore it's going to have 16.3% hydrogen. Now these percentages, we can pretend like we have 100 grams of the alkane, and we could take these percentages to just mean mass. So we'll have 83.7 grams of carbon in this alkane, 16.3 grams of hydrogen in this alkane. Therefore, to work out our moles, we can work out or the number of atoms of each element in this alkane. We can divide it by MR. So divide it by MR to find out the moles. Then once we've got our mole ratio, we can then divide by the simplest number or the smallest number, and that is 6.9 here. So 6.9 divided by 6.9, we get 1. 16.3 divided by 6.975, we get 2.33. Now this we can't just round up or down, which a lot of people did. We have to get rid of this this fraction here by timesing both numbers. And we can times by 3 to get rid of that, and we get 37. Now it is worth knowing that that it would really help you to know what these 0.33 what the decimal is in fractions, so you can times it by the correct number. So if you know 0.33 is a third, you know that you've got to times this by 3. If you know that 0.16 is a sixth, then you have to times it by 6. Same again, if you know 0.11 is 9, then you have to times both by 9, and you can do that right the way up to 20 really. So you shouldn't really be rounding up any numbers if above or below 0.5. So 0.05 should be the minimum that you round up. Okay. Next one. We have the molecular mass of this is 86 grams. We have to find the mass of C3H7, which is 43. This means that we have two lots of these. So if we times this by 2, we get our molecular formula there. So we're going to draw two structural isomers of C7H16. So we're going to have 7 carbons in total. One isomer should have an ethyl side chain. Therefore, we should draw 5 carbons first, a 5 carbon chain length, and then add our ethyl group next. So 1, 2, 3, 4, 5. And then we can add our ethyl group. We can't add it here. That's because it becomes part of the parent chain if we do. And then that's probably going to be the same for this the other side of this carbon as well. We can't add it either of those two positions, so it can only go in the middle. Therefore, our ethyl group is on the 3rd carbon, and we have 3 ethyl pentane. Then same again here. This one needs 3 methyl groups instead, so we're going to draw a carbon chain of 4 first. So 1, 2, 3, 4. Then we're going to add our 3 methyl side chains. And it doesn't matter as long as 2 are on one and then 1 is on the other. And the lowest number is 223 trimethylbutane instead of 332 trimethylbutane. So it can only be that. So in your cyclic and branch chain alkanes, the intermolecular forces are weaker. And that's because they can't pack together as closely. They're therefore more volatile, so they ignite better, and that's why you get more efficient burning. And in this question, we've also answered in terms of intermolecular forces. So if a question ever says in terms of intermolecular forces or anything else, you have to use that word, the key word that they've expressed there. You have to use it in your answer. Here you have the formation of cyclopentane, which you draw here from pentane, using skeletal formula, and then you just need to remember that hydrogen is also the other product. Here for cracking of indicane, two conditions are high temperature and catalysts. You have to include those. It tells you heptane and ethane. So if you write heptane and ethane, then you can minus those 2 molecules from this molecule to get whatever's left over, or to calculate whatever's left over, and that would be another ethene molecule. Now in alkanes, your carbon-carbon double bond is very strong, and your carbon-hydrogen is very strong, and that's why ultraviolet light can't break these down. It only breaks down the halogen in our free radical substitution, because these have higher bond energies. So your answer here is D. So in a combustion reaction with an alkane, or any type of combustion reaction for that matter, you're always reacting with oxygen, which is O2, and you always get the same products, which are carbon dioxide and water. Then you just need to balance. When balancing, I always balance the carbons, then the hydrogens, and then the oxygens last, because the oxygens are found in the greatest number of places. So they're the most difficult to balance. And sometimes they do just balance out for us. So I always draw this table on the side there to help me when balancing. Now, upon combustion, we always get a mixture of products, and we have sulfur impurities in fuels. So sulfur dioxide can be produced from oxidation of the sulfur impurities. Your unburned hydrocarbons can also be produced if there's not enough oxygen, and then same with carbon. Then hydrogen is the one that's left over. Hydrogen is never produced. It's extremely flammable, so it will never be produced in combustion. D. This question is a biology link. Your carbon monoxide bonds irreversibly to hemoglobin. That means once the carbon monoxide has bonded to your red blood cell, you can't use that red blood cell anymore. Your body actually has to get rid of it, which I think red blood cell replacement takes around 90 days or up to 90 days. So the answer is it binds irreversibly to hemoglobin, reducing the oxygen carrying capacity of the blood. Now, nitrogen oxides are produced when the nitrogen and the oxygen are already in the air. The engine offers the high temperatures, or the activation energy, to cause these two to react with each other. So those are your 2 marks. Your oxides of nitrogen can then go on to dissolve in rainwater to cause acid rain. You get 1 mark for that. Then your second mark is for being specific with the type of damage it causes in the environment. So it either damages trees, fish, buildings, changes the pH of rivers and lakes, or any other words to these effect, like damage aquatic life or organisms. Nitrogen and carbon monoxide react together in catalytic converters. They produce nitrogen and carbon dioxide. When balancing the equations, I'd always balance the oxygens last because they're in the most number of places. And then ensure that your nitrogen is diatomic. Hydrogen, nitrogen, oxygen, and all of your group 7 are the diatomic molecules you need to know. Your catalysts found in catalytic converters are rhodium, platinum, or palladium. Some people put honeycomb, which is a structure, not a catalyst, and some people put zeolite, which is used for catalytic cracking, instead. So you get your first mark for this last one by saying no, carbon dioxide is still produced, or no, carbon or unburnt hydrocarbons are not removed. And then you get the second mark for saying why they are a pollutant. So you get 1 mark for explaining why they are a pollutant. So here it says state and explain 1 advantage and 1 disadvantage of using biofuels to replace fossil fuels. So you'll get 2 marks you'll get 1 mark for stating your advantage and then 1 mark for explaining it. And each bullet point is a state and explain pair. So your first part, before the / I've put the state answer, and then after the / I've put the explain answer for the advantage. And I've done the same for your disadvantage as well. Now your examiner might accept some other answers which are sensible, but try to stick to these main ones in an exam.